Okay, so in the previous class, we were looking at fixed length source coding. Having spent some time talking about variable length source coding, we moved to this other problem where for now we're assuming that we have an IID source sequence of length n drawn from some distribution Px, which is given to us. And the goal is to compress this to a k length code word sequence such that you are able to recover xn with high probability. And when I say high probability, I mean that the probability that the decoder outputs something that is not equal to xn is vanishing as n tends to infinity. All right. And here k is fixed, which can depend on the distribution px or pxn, but is independent of the realization of the source sequence. And we define the rate as before to be k over n. All right. So for this, we saw two different compression schemes. One is the optimal compression scheme, wherein once you fix a k, basically what you do is list the sequences in decreasing order of probability, make a table of the top 2 to the k sequences, and then only encode those correctly. All the other sequences which don't lie in the top 2 to the k sequences are all going to be mapped to the all zeros code word. So the probability of error would then be just the probability that it is not in one of the top 2 to the k sequences, and if k is large enough, then the probability of error will be sufficiently small. But so far we've not seen a proof of what is the smallest k or what is the smallest r, which ensures that the probability of error vanishes as n tends to infinity. And we'll see that later in this particular class. But then we saw another compression scheme which operates in the following manner. So we first construct this epsilon typical set, which is the set of all n length sequences for which the empirical frequencies are all close to the probabilities of the corresponding symbols to within an epsilon. All right. So using this particular notion of an epsilon typical set, we can construct a compressor in the following manner. Basically, now you construct a table of all possible sequences in the epsilon typical set, and you assign code words for each of those sequences. And if it does not lie in this particular epsilon typical set, then that particular source sequence gets assigned the all zeros code word. So an error occurs only if the sequence is not epsilon typical, right? And the rate that you require is basically 1 over n times log of the size of the epsilon typical set. And in the last class, we saw that the probability of error for the epsilon typical set for any epsilon greater than 0 is exponentially decaying in n. Right. Specifically, we use the Chernoff bound to show that the probability of error is basically this particular quantity. And then we also saw what the size of the epsilon typical set should be. It is roughly 2 to the n times the entropy. All right. And in deriving bounds on the size of the epsilon typical set, we proved a number of other properties of the epsilon typical set. For one, we saw this kind of an averaging result, which says that if you take any epsilon typical sequence, then the empirical frequency of any function g is within an epsilon of the corresponding expected value of g. All right, and we use this to show that for any epsilon typical sequence, the probability of occurrence of that particular sequence is almost equal to 2 to the minus n times the entropy. And using this, we showed that the size of the epsilon typical set is roughly 2 to the n times the entropy, where the exponent is within a 1 plus or minus epsilon. Right. So basically, this essentially says that the rate of this compressor that is constructed using the epsilon typical sequence, the typical set compressor, achieves a rate that is within an epsilon of the entropy. All right. And now what we want to know is this the best possible? Is it possible to construct a compressor for which the rate is strictly below the entropy? And we'll basically show that no, that is not possible. All right. So let's see how to prove that. So now we have two sets, T n epsilon of Px, which is the epsilon typical set, and we also have B. I'll define this B n epsilon of Px, which is the set. So basically you list the sequences, the source sequences, in decreasing order of probability until the probability of, let me call this Bn delta of Px, which is the smallest set with probability 1 minus delta. So it's at least 1 minus delta. Right? So equivalently, it says that the probability that xn does not lie in Bn delta of Px is less than delta. And how do you construct this set? You basically list all of the sequences in decreasing order of the probability. And you keep going down this list until the total probability is at least 1 minus delta. As soon as it exceeds 1 minus delta, you stop. All right. So you list the sequences in decreasing order of probability. And then you list the top k sequences such that the total probabilities is just more than 1 minus delta. All right, when it just exceeds 1 minus delta, you stop. So if you remove any sequence from this list, then the total probability is less than 1 minus delta. If you add another sequence, it is greater than or equal to 1 minus delta. So that is my set B n delta of Px. Right? So clearly, if I want to make sure that the probability of error is at most delta, then what is the minimum rate that I can possibly achieve? So if we want the probability of error to be, say, less than or equal to delta, then the minimum compression rate what would this be? In terms of B and delta, or whatever we've seen so far. Correct. So Bn delta is the smallest set which has probability 1 minus delta. Right? So if you want to encode sequences, some subset of sequences with the least possible rate, which is essentially with the least possible cardinality, then you should choose your set to be Bn delta. If you choose any other set, then the corresponding rate is only going to be higher, because by definition Bn delta is the smallest such set. So this is 1 over n log cardinality B n delta of Px. So if we are able to get an upper bound on the cardinality of Bn delta, then we also have an upper bound on, a lower bound on the cardinality of Bn delta, then we also have a lower bound on the minimum possible rate required for a certain target probability of error. Right? Okay. But we also know that if we choose the typical set, then the probability of error is something that is vanishing with n. Right? So let's do the following. Let's fix an epsilon greater than 0. This epsilon is taken to be something very, very small. I want a lower bound on the cardinality of Bn delta. Right? But the cardinality of Bn delta is going to be greater than or equal to the cardinality of Bn delta intersection Tn epsilon of Px. Okay. Great. So let's keep this aside. Now what can I say about any sequence in this particular intersection? Let me call this set A, or maybe An. So first, I want to bound the size of An, but I'll also try to find out what is the probability that Xn is not in An. Okay, so this is the probability that Xn is not in Bn delta, or it does not lie in the typical set. Right? So for the union bound, this is less than or equal to the probability that Xn is not in Bn delta, which is delta, plus the probability that Xn is not in Tn epsilon, which is something that vanishes with n. Right? And we saw that this is less than or equal to cardinality of x, I think 2 times cardinality of x times e to the minus n epsilon square p min by 3. Right? Great. So in other words, the probability that Xn is not in An is greater than or equal to 1 minus delta minus 2 times cardinality of x e to the minus n epsilon square P min by 3, which is just 1 minus delta minus little of 1. Remember that our goal is to construct a compressor for which the probability of error, which is delta, is also vanishing in n. So basically we want this quantity to be 1 minus little of 1. Right? So let's write this down. So probability that xn is in an. So 1 minus delta minus little of 1 is less than or equal to the probability that xn is in an, which is summation over all sequences xn in an pxn of xn. Right, I've done nothing here, I've just expanded this out as a sum of probabilities of individual sequences that lie in the set an. But now what is an? It is the intersection of b and delta with t and epsilon, which means that every sequence that is in an should also be in t and epsilon, right? But we've seen that for any sequence in t and epsilon, the probability of occurrence of that sequence is roughly 2 to the minus n times the entropy, right? So in particular, this is less than or equal to xn in an 2 to the minus n times the entropy times 1 minus epsilon, since xn must lie in t and epsilon, and therefore satisfy that property that we had proved earlier. So this is nothing but the size of an times 2 to the minus n times the entropy times 1 minus epsilon. So the size of an is at least 1 minus delta minus little of 1 times 2 to the n times the entropy times 1 minus epsilon. But we've also seen from this particular equation over here that the size of b and delta is at least the size of an. Which means that the minimum rate of compression for a given probability of error delta is at least the entropy, or n times the minimum rate is n times the entropy times 1 minus epsilon plus log 1 minus delta minus little of 1, or the minimum rate for a given probability of error delta is at least the entropy times 1 minus epsilon plus 1 over n log 1 minus delta minus little of 1. All right, and this epsilon was something that's arbitrary, right? I just chose it to define the epsilon typical set. And this whole line of reasoning works for every epsilon greater than 0. Therefore, the minimum rate must be greater than or equal to the entropy plus something that is vanishing as n tends to infinity.
After summation, is A and dash?
Which one?
After the summation.
After the summation. So here, right? Okay. Okay. I'm sorry. I think that's just it's size of an times this. So the minimum rate of compression is entropy, right? Asymptotically, for large enough n, you cannot achieve a rate that is below the entropy. Right? Any questions? Okay, great. So now let's our first goal will be to extend these ideas to think about not just lossless compression but also lossy compression. Right now the goal was we have an xn, we want to compress this with the objective of recovering xn exactly. Now in problems such as, let's say, speech or speech audio or video or image compression, you don't really worry about recovering the source exactly. It's okay to allow a little bit of distortion between the reconstructed sequence and the original sequence. So for this, if I say that I allow a certain amount of distortion, then what is the minimum rate of compression that I can possibly achieve? Right? But before we go to that, we'll see one other property of these typical sets, which we'll use subsequently when we talk about both lossy compression as well as later on when I talk about channel cooling. All right. So let's say that I have this set Tn epsilon, but then I observe, so I have a PMF Px that I choose, but then I observe a source sequence xn which is distributed according to Qx, which is different from Px. So if the true distribution is IID distributed according to Qx, what is the probability that this sequence belongs to Tn epsilon of Px? So it's a typical set for a different source or a mismatched source. Okay, since we've already seen the high level techniques beforehand, you can suggest how I should go about this. What would be the first step? Right now you know all of these properties of typical sets, right? The main properties that you keep reusing are the following. First, every sequence in the typical set Tn epsilon has a probability that is roughly 2 to the minus n times the entropy. You also know that the size of the typical set Tn epsilon is 2 to the roughly 2 to the n times the entropy, right? Entropy of Px. But remember, the actual distribution for Xn is Qx, not Px. So how should we go about bounding this particular quantity? What do you think? Yeah? Well, you're hinting at what the final solution should be, but let's go step by step. How would you start analyzing this particular quantity? What would be the first step? Yeah? Okay. Very good. So let's write this as a summation overall xn in Tn epsilon of Px times the probability of occurrence of one of these sequences, right? But what is the actual probability of occurrence of xn? One particular sequence. It's Qxn of x, but this Qxn is just IID Qx. All right. Okay. What do you think you could do next?
Multiply and divide.
Okay. So I'll give you a hint. So now you have this distribution Qxn, right? I should say Qxn of xn. Now if this were Pxn of xn, then I could directly use the probability that each sequence xn has empirical frequency that is close to Px. Right? That's basically what I want to use. I know that for any sequence in the typical set, the empirical frequency of that particular sequence is very close to the probability itself. All right? So is there a way of writing this particular quantity in terms of the empirical frequencies of the symbols in Xn? Yeah?
Expectation of 1 over n minus sigma xn.
What is?
Expectation of 1 over n times sigma times the indicator variable.
Okay. I mean, that's the empirical frequency, right? But here I want to write this probability using, I want to express this as some function that involves the empirical frequencies. So maybe let me write another step. This is equal to product I equal to 1 to n qx of xi, right? Is there a way of rewriting this that captures the frequencies of occurrence of various symbols in the alphabet, in the particular source sequence
Write it
xn?
as sigma x over the alphabet.
Uh, Not sigma, product, right?
Empirical frequencies over the whole sequence, right? Xn.
That's the empirical frequencies. I want to express this quantity as a function of the empirical frequencies.
You can write the above summation itself as sigma x over the alphabet qxn times the empirical frequency.
Which
Three
one?
times empirical frequency.
Sorry, which one?
The above summation.
This summation.
Yes.
Not real, right? This is a summation over all possible sequences in the typical set. Right? The right way is, okay, let's look at this particular quantity. Right? This is a product of n terms. Right? It's qx of x1 times qx of x2 times qx of x3 times so on. Let's take a simple binary example to see how this would look. Right? So if I have 1 0, let's say I have the following sequence, say 1 0 0 1 1 0 0. Then this is my xn. My qx of xn would be qx of 1 times qx of 0 and so on, qx of 0. Right? That's one way of writing the probability of occurrence of this particular sequence 1 0 0 1 1 0 0. But then if you look at this particular quantity, there are only two distinct terms, right? They basically repeat. So this is equal to qx of 1 cube, right, times qx of 0 whole to the power of 4, because it repeats 4 times. So if I have a quantity of this particular form, right, with over some alphabet, right, or in general, let's suppose that I have the alphabet size is 2, it's zeros and ones. What would this quantity be equal to? It would be qx of 0 raised to basically number of times 0 occurs, which is n times mu of 0, times qx of 1 raised to the number of times 1 occurs in the sequence. So the probability that xn lies in Tn epsilon of Px is equal to sum overall xn in Tn epsilon of Px times the product over all possible symbols in the alphabet of the probability of occurrence of that particular symbol raised to the number of times that particular symbol occurs in the sequence x1 through xn, which is mu n times mu xn of x. Right? Is this fair? Great. So this quantity, right, so now I have things expressed in terms of quantities that I can very easily bound. What can I say about mu xn of x? I know that each xn lies in T n epsilon of px. So each mu xn should be close to px. So this is upper bounded by xn T n epsilon of px product overall x qx of x raised to n times px of x times 1 minus epsilon. Because okay, I should really write this as 1 over qx raised to n times mu x, because qx is something which is less than 1. So if the exponent of that, since qx is less than 1, if the exponent is larger than the quantity is smaller. Okay, so this is less than or equal to sum overall xn in the typical set two raised to n times px of x log qx of x times 1 minus epsilon. Right, I just wrote qx of x as 2 to the log qx of x. That's all, nothing else. So this is equal to of px 2 to the power summation overall x n px of x log. Oh no, it's not inside the log, it's outside the log. Times 1 minus epsilon. Okay. So I'll since the exponent is, I'm going to see many exponents of this form where the exponent itself is a summation of various quantities. Instead of saying 2 to the something, I'll write this as exp2, which basically means 2 raised to something. So the exponent is n times px of x. I'll write this as minus log 1 over qx of x times 1 minus epsilon. So this is equal to the size of T n epsilon of px, because this whole quantity over here is no longer dependent on the sequence xn. I can basically take it outside the summation. So it's a summation of 1s overall xn in t n epsilon px, which is the size of t n epsilon of px, times 2 raised to minus n times 1 minus epsilon sum over all possible x n, sorry, there's no n, p of x log 1 over q of x. But now what do we know about t n epsilon of px? Size of t n epsilon of px. That's roughly 2 raised to n times the entropy of px times 1 plus epsilon, right? So this is less than or equal to e to the power n times the entropy of px. So let me expand that out. Minus what is remaining here, which is n times 1 minus epsilon right? Any questions? I'll write this as minus n times 1 minus epsilon px of x log 1 over q of x plus log px plus this some other term but it's something that is very small because it's n times some constant times epsilon. But then what is this particular quantity? It's just the KL divergence between px and qx. So this is equal to n times the KL divergence between px and qx times 1 minus epsilon plus 2n epsilon times the entropy of px. So this will be a negative sign here. So the probability that xn, which is distributed according to qx, lies in the typical set corresponding to px decays as 2 to the minus n times the KL divergence between px and qx, right? Which is logical if you think about it, because if px and qx are very different from each other, right? So the farther apart px and qx are in terms of KL divergence, then the empirical frequencies of xn, because it's distributed according to qx, it should be very close to qx. It shouldn't be very close to px, right? So the probability that the empirical frequencies of qx, of xn distributed according to qx, will behave like the empirical frequencies of px should be very, very small. And this probability should become smaller and smaller as px and qx are farther apart. All right, any questions? Okay, so let's make note of this. So now let's look at the lossy source compression problem. Wherein we're okay if the reconstructed sequence is different from the actual source sequence all the time. But then it should be within some limits. So how do we model this particular problem? We're given xn, and for now, again, we'll assume that xn is an IID sequence. We'll also assume that xn is discrete, so the alphabet is finite. We'll see how to extend this to the case where the alphabet is infinite later on. All right? Because that's really, when you say lossy compression, that's typically the regime that you're interested in. The source sequence would be from some continuous alphabet, and you want to discretize this. This is, for example, what you would see in an analog to digital converter, where you observe some signals, maybe these are wireless signals or speech signals or images, which have continuous alphabets, and you want to represent these using a finite number of bits. So we'll assume that this is IID Px. The goal is to encode this to a compressed sequence, where again this k is fixed. Such that when decoded, you get an xn hat but now I'll also allow this alphabet x hat to potentially be different from x. All right, the source sequence lies in some alphabet xn, and the reconstructed sequence maybe lie in a different alphabet than xn itself. Okay, so here is one such example. Maybe the signals that you observe x is maybe these are integers, right, just as a toy example, and you want to compress them to maybe the following two symbols, minus 2.5 and plus 2.5 for whatever reason. In this case, the reconstruction alphabet is different from the source alphabet. Okay, because the source alphabet was just a set of integers from minus 10 to plus 10. The reconstruction alphabet is only the two quantities, minus 2.5 and plus 2.5. This is just a generalization. Sometimes the source alphabet, the reconstruction alphabet, could also be equal to the source alphabet. Or maybe it could be a subset of the source alphabet. It depends. It varies from application to application. But this is the most general form. We will allow x hat to potentially be different from x. All right. Now, in addition, I also have a distortion measure, which is the following. So, d x hat is a so basically d is some function that takes an input symbol and a reconstruction symbol and outputs some real number. We'll assume that these are non-negative real numbers. So one such distortion measure is the absolute value of the difference between x and x hat. All right, so this is the absolute error measure. dxx hat could be x minus x hat squared, which is the squared error distortion. Or it could be equal to 1 if x is not equal to x hat and 0 otherwise. Which is called the Hamming distortion. So when you're defining a lossy compression problem, you also have to specify what is the distortion measure you will use. All right. So the goal is to construct this compression scheme, which is to construct the encoding algorithm and the decoding algorithm such that the expected distortion, which is 1 over n, summation the distortion between xi and xi hat, this quantity should be less than or equal to some number capital D. So this is the amount of distortion that you're willing to tolerate. So for example, if you are working with the absolute error distortion, this basically says that the mean absolute error distortion should be at most capital D. If you're using squared error distortion, then you're saying that the mean squared error should be at most capital D. If it's the Hamming distortion, then you want the average Hamming distortion to be at most D. Right, so this quantity is sometimes called the per letter distortion. And as before, we'll define the rate of the compression scheme to be K over F. So the goal is to construct a lossy compression scheme for which the distortion is at most D and the rate is as small as possible. And our goal is to find out what is the smallest rate that we can achieve for a given target distortion D. So I fix a particular D. I want to know what is the smallest value of R that you can achieve. All right. So here we'll make a couple of assumptions. We've already assumed that the alphabets are all finite. And throughout we'll assume that this dxx hat is bounded by some number d max. Right? So this distortion measure is going to be a bounded distortion measure, even when the x and x hat are infinite. We will still make this particular assumption. Okay. So before we actually see what or try to derive what is the smallest possible R, let's try to think about what a lossy source compression scheme would potentially look like. Okay, so I have this space which is Xn. This is where all the source sequences are coming from, and I have Xn hat. A set of all possible reconstruction sequences. Now I want the rate to be something small, right? Which means that if I fix a particular R, then I have 2 to the nr possible sequences, right? Which can be represented using those nr bits. So this means that there's going to be some subset of reconstruction points that is going to be output by the decoder. The decoder is only going to output one of these 2 to the nr possible sequences from xn hat, nothing else, right? So the reconstructed sequence xn hat can only be one of these blue points. and the goal is to design a mapping. So what should effectively what should the encoder and decoder do? You should design an encoder and decoder such that all of these points from xn, each point in xn gets mapped to one of the corresponding blue points. All right. And if you think about it, intuitively, you should be designing this map so that all of the points in xn that get mapped to the corresponding xn hat, loosely speaking, you should map each xn to the, so to speak, closest point in xn hat. Right? It's kind of logical. Right? Because if you are not doing that, then you would incur a higher distortion. So if you fix a particular xn, if you fix a particular set of reconstruction sequences, then the most logical thing to do would be map each sequence xn to the closest point in xn hat. When I say closest, in terms of this distortion measure. The distortion measure is not necessarily a metric, but then whichever point gives you the least distortion. All right? Does that make sense? So for example, all of these points would get mapped to this particular xn hat and so on. Right? So every xn gets mapped to that xn hat, which minimizes the distortion. And I'm using this as short form to basically indicate 1 over n summation d of xi hat. Maybe. So this quantity, the set of all possible reconstruction points that we have, we'll call this the code book. All right. So basically, constructing a lossy compression scheme can be decomposed into two things. One, you construct a code book, which is the set of all reconstruction points, the 2 to the nr reconstruction points. And the second is the encoding. How do you map each source sequence to the corresponding reconstruction sequence or code word in the code book? Okay, so each point in this code book can be represented using nr bits, because there are 2 to the nr sequences. Right? And how you map them to binary is not particularly important right now. There could be a computationally efficient way of representing them in binary, but we're not going to worry about all of that now. Okay. So Is the problem and the setup clear, or are there any questions? Okay. So the way we'll go about this is, what we could do is try to look for the optimal scheme. Right? You find that code book and that encoding which minimizes the distortion for a given R. But then we'll go for a suboptimal scheme, which eventually it will turn out that it is asymptotically optimal. And we'll use the same set of ideas that we developed for the lossless compression problem. Right? So right now I'm going to be introducing a bunch of new conceptual ideas. So firstly, remember that the code book is, so I have to specify what the code book is, and I also have to specify what the encoding is. Right? How do I choose the code book? One way is I could look for the optimal code book. Maybe design this, I could search for the optimal code book for a given distribution Px. But instead, what I do is I'll construct a completely random code book. All right, I'll pick a distribution and I'll pick a sequence of 2 to the nr code words that are randomly distributed according to that particular distribution. All right. And how do you, the encoding, again, I know that for a given code book, this is the optimal encoding, but then I won't do that. I will use a suboptimal encoder. And I'll do all of this just so that I can analyze it easily. All right. If I look at the optimal code book and the optimal encoder, it becomes harder to analyze analytically. But then just for the sake of analysis, I'll take a completely random choice of code book and a suboptimal decoder. And we'll see how well that performs. All right. So first, I'm given this distribution Px. All right, I will pick a conditional distribution Px hat given x. All right, such that the expectation the expected distortion between x and x hat when x hat are jointly distributed according to Px hat, this is less than or equal to d divided by 1 minus epsilon. D divided by 1 plus epsilon. This is a little smaller than d. My target distortion is capital D, but then I'm going to back off from that by a little bit, and I'm going to pick this conditional distribution Px hat given x that satisfies this. Okay, remember that this whole quantity is independent of n. So this quantity is just summation over all possible x and x hat. Okay, so this quantity should be less than or equal to capital D divided by 1 plus epsilon. Okay, you pick any Px x hat given x that satisfies this property. Later on, we'll try to optimize over the Px hat given x also, but for now, let's pick one such Px hat given x. Now, corresponding to this Px hat given x, there is a corresponding marginal distribution Px hat. right? The way I'll construct the code book is I'll take 2 to the nr sequences where each component is chosen independently and identically distributed according to px hat, right? So I'll choose a code book which is going to be x hat to the nr. I can potentially write this as maybe an n times 2 to the nr matrix, right? Where each entry of this matrix is IID px hat. So each x hat j x hat, the ith component of the jth code word is IID px hat. Okay, it's a completely random choice. So obviously you shouldn't expect this to be optimal, right? So that completely specifies the code book, right? Now I'll also define a typical set. But now the typical set is not for one particular random variable, but it will be for a pair of random variables. Which is the set of all xn hat such that the empirical frequencies are all close to the corresponding probabilities. And one thing to keep in mind is that this mu xn hat is basically the number of, or the fraction of locations where xi is equal to x and x hat I is equal to x hat. So this is called the joint type between xn and xn hat. So in this, as well as in the previous discussion on lossless compression, the high level idea is the same, that when you go to high dimensions, if you see, let's say, an IID sequence, then the empirical frequencies are all going to be close to the true source sequences, right? The true probabilities. And in this case, that's also what we expect here. So if I take two pairs or two IID sequences of correlated random variables. So in this case, I have xn and xn hat, where the components are all IID, but each pair xi hat is distributed according to Pxx hat. So if I have such a pair, then the joint empirical frequency should also be close to their true probabilities. Again, nothing conceptually new, it should just follow from the law of large numbers. Our goal will be to make use of this property, this property that in high dimensions all of the empirical frequencies are close to the true probabilities in order to construct the encoder for our lossy source code. Alright, so the encoder will work as follows. So you take a particular xn.
Shouldn't that be indicated xi equal to xn, xi hat equal to
That's right. This should be xn. Correction. Alright, so for each xn, the encoding of xn is going to be equal to the smallest I in 1, 2, 3 up to 2 to the nr such that xn is jointly typical with xn hat of, sorry, let me not use I, let me use j over here. Alright, so the conditional distribution Px hat given x only appears in this construction of the encoder. It does not occur anywhere in the construction of the codebook itself. So the codebook is constructed according to Px hat, and the encoder basically says that you map each xn that is typical to that corresponding xn hat. If there are multiple sequences, if there are multiple code words that are also typical, that are jointly typical with xn, you map it to one such code word. And in this, here I have this rule where I encode it to the smallest in the order of code words. And the first code word with which it is typical. That's it. All right. Now this is different from the optimal encoder. In the optimal encoder, I would basically say that you map each sequence to the closest code word in the code book. When I say closest, in terms of distortion. Here, this is basically saying you find the first code word that is, loosely speaking, within distortion D of the corresponding source sequence. Which could be suboptimal, but that's still okay. Right? Right, so here my claim is that the expected distortion between xn and xn hat is going to be less than or equal to d into 1 plus little of log. which seems a bit surprising because essentially all I've used is typical sets and I have chosen a completely random codebook, right? But then it turns out that even though I have chosen a random codebook, with high probability, it's still going to perform very, very well. Okay, so let's stop here. We'll continue in the next class. Any questions? Yeah. I'm sorry?
Joint type formula, the new one.
This one, yeah. I'm sorry?
What is it actually?
So here, let's say you observe this sequence, right? I have two sequences. All right? You look at these pairs of symbols and find the frequencies of occurrences of these pairs of symbols. So for example, how many times does 0, 0 occur? In this case, there's only one occurrence of 0, 0. So the joint type of x, x hat would be 1 divided by 3, 7. So it will be 1 by 7. Right? Similarly, what is the frequency of occurrence of 0, 1? I see here there are two occurrences. So that's 2 divided by 7 and so on.